So hello everyone, my name is Liz and welcome to Community Conversations. This is an opportunity for you, the community, to hear from contributors within the internet computer ecosystem and ask them questions live. So in today's community conversation, we have staff engineer Paul Liu, who's going to walk us through how to build a Dapp on the internet computer in the Motoko programming language. So without further ado, Paul, feel free to take it away.
Thanks, Liz. Hi, my name is Paul. I work at Dfinity. Previously, I built a game application called Reversey on the internet computer. It was one of the early games built on the platform. So instead of, going through the application itself, I'm just gonna share some of the I think it's worthy topics for developers who may be new to the platform or who may get started with Motoko. So for this session, I assume you know a little bit basics about Motoko, the language. So I'm not going to dive into those syntax and all that. And maybe you have some background knowledge of how the internet computer works, but you might also have a lot of questions, so we'll start from there. In general, a Dapp architecture on the internet computer is that we have a user as a front end, has a front end, which can just be a browser. The browser will be able to visit some URL, like here's a URL with some cancer id.ic0.app. So this will direct the user to your application. So where is your application? Your application is actually running in Canister, which is a concept of similar to a lightweight container. So it has all your program code or your program state, and it communicates, is able to communicate with the front end. And it also communicates with other canisters on the same internet computer. So if we think about, this not just as a blockchain, but as a high-level abstract kind of concept, it's more or less just a virtual computer where we have programs built by developers, they deploy to the virtual computer, and this program just run forever. So that's the way I like to think about it. So these programs, they are self-encapsulated in this canister. They communicate with each other, and they can deliver messages among each other. They can also deliver messages that gets translated to HTML and JavaScript to the front end. So the front end can, after receiving this HTML, can render it and can run the JavaScript in it. The JavaScript can make a call to the backend, canister over HTTPS. So a little bit more detail about this typical architecture of application. Often we have a asset canister that serves static assets. So that's the URL. When you visit that URL, you're gonna hit this canister. The browser will just resolve this URL, and the first step is to download the service worker. The service worker does takes over from here. So the service worker will download further things like will make queries to your asset canister and download the mem page and verify that. Not only download that, but also verify that. Sometimes we see people use canister id.raw.ic0.app. That's directly accessing the asset canister. That's without the service worker. So we'll get into this verification thing a little bit later, but it's good to know that the difference. So the service worker will load the assets. The assets are all coming from the asset canister. And after loading the assets into the browser will start to run the JavaScript. The JavaScript is then free to call any canister on the internet computer. So it's not restricted to only your application. It can call to other applications as well. So when it makes the call, it's basically an asynchronous request sent to the internet computer, which is then routed to your canister. Your canister makes handles the request, gives the response, and the response is routed back to the user browser. A typical backend service will look something like a collection of basically functions. So this example I took from my Reversi backend canister. So it has a couple, you can see there's a couple functions. You can register a new user and it return you some result. So this format is called candid. Candid can be automatically generated from your Motoko code. So this is all handled by the SDK. You don't have to explicitly worry about those. Yeah, basically this notation denotes a function. So there's register methods and there's view method is gonna return you some game view, which is an option, and it's marked as a query. So we can see there are two queries, and the others are not marked as query. We'll get into the difference between query and update calls. So those are not marked, are considered update calls. These types, they are also described in candid. So here's the example of a variant type, which is basically enum. You can have a couple different options like game not found, game not started, and game over. It actually has an argument, can carry an argument with this option. So I won't go into the detail of candid, but every canister, when you compile it when you compile it from a Motoko file to a canister, you are declaring a set of services of this canister. And when this canister is deployed to the internet computer, this is its interface with the list of functions you can use and a set of types. So you can also discover canisters, other people's canister on the internet computer and look at their interface. Then you can find ways for your code to make use of that, to call into their canisters. The difference between query and update call is in how they are implemented. But when you use it, there's some performance difference. For example, the query call will take like anywhere between 1 to 3 seconds, but update call will take 1 to 3 seconds. Query call is very fast. It's just on a millisecond level. So if you add the network transportation time to it, then this is really, query call will be really similar to the web we know. When you make an HTTP request, usually it responds in 100 milliseconds or less. But query call, there's other notable characteristics. Update call, as we know, for in a actor programming model, actors have its local state. When you want to mutate the state, you have to send it a message, right? This message is handled by interface of the actor. So then the actor will run, will modify its own state, then maybe give a response. On the internet computer, the state change of the actor is persisted. So, which means the actor runs in a single thread. It handles one call at a time. That's the traditional actor model. But in canister, we roughly say it's basically an actor, but there are some other things. One of them is query call. So canister can run query call. There are methods you can declare as queries. When they run, they discard all the state change. So it means it won't change the canister state, which means it can run in parallel. It can run concurrently. We can concurrently serve many requests at the same time because they can just run in their own copies since they don't change the state, which is another aspect of this difference, whether they're executed in parallel or in a single thread. So query call is fast, but there are several concerns. One concern is because query call is executed by a single node in the subnet. And we route it to basically a random node in the subnet. But this node may not have the latest state because all the nodes are constantly computing, right? They're participating in consensus. They may update their states at different times. So if you're unlucky, you hit a node that's a little bit behind, this node is not going to have the latest state for your chemistry. So when you make a call to it, when you make a query call, it may not be executed against the latest state. So it could return some old results, which may come as a surprise because we don't usually have this behavior in the traditional web architecture. The solution here is your application has to deal with it. So in my game, when I query the game view, I use query call. I want it to be fast so that I can render the game board to the user fast. But if I just take the board and render it, if it has an old state, so I render previous rendering, maybe using a later state than the next query I get. So the next query may get return old state. If I render the board like that, the user will be, suspecting your game is broken, that has a bug or something, right? So the way I deal with this is I introduce another field which keeps all the historical moves. So this list of moves by both players is only going to increase. So by just checking the length of this array, I can make sure my front end only render the latest game view. So if I receive something that has less moves than what the front end already knows, it will just discard that. So that's a common trick. You can use a counter here, which will work as well, but I use a list of moves because I want to verify whether the board is correct, which has to do with the next point. So query call may be answered it's answered by random node, but this node may be adversarial, right? You never know. So which is why we have to run consensus among all the nodes. As long as majority is honest, then we can know the update calls, they are executed correctly. But for query call, it's hard to know that. So to guard against, something being returned wrongly, there's basically two ways to deal with it. One is just switch back to update call. If you have very critical data, you don't want to mess up with the user display, then the suggestion here, the simplest way is just make an update call and handle that latency in your front end. The other way is to use certified data or certified variables. This, at the moment, Motoko only has very limited support. So if you want the best support, you probably have to go with Rust, which has some low-level support for it. Yeah, in that case, I won't go into this in this talk. So, but if people are interested, there's a recent update gave a low-level access in Motoko library to use certified data. But that's another way. If you certify your assets or your game state in the previous update call, later on you can use query to fetch that certified data. Then the client can verify this has been, this is truly from your cancer state. The node cannot mess with it because it has a signature on it. So that's one thing the service worker do. It fetches fetches data from your canister and verify their certification and signatures. Another thing you might want to do in your game, not game, in your app, is to somehow have access control. Who will be able to call your methods. So here is an example of the register function I implemented for the game. It used this message caller. So the message caller will be the user who is making this call. So we can see this is a update call. The user will register, will call this function to register to register its name, and we can directly fetch the caller, and then what it does here is just look up player by ID. The caller ID, the player ID, if it's already registered, then we just return an option saying it has already registered. The notation here is to use the shared keyword followed by some argument. This argument refers to the entire message, and it has an extra field called caller. So update call can get this security because the blockchain has already verified the caller. In case of a user making this call, the user would have already signed this message at front end and send it to the back end. When the blockchain receives the user message, it would have already verified the signature is correct. Then we can trust this caller field to be secure. But if it's query call, then the malicious node can basically manufacture any signature it wants, right? It doesn't even have to manufacture the signature. It can just execute your canister and run it with a different caller. So query call is only secure if the call is answered by an honest node. So which is, again, an important point. We have to remember, if we want security, we better either use update call or use certified data. Another interesting thing in Motoko is that you can have actor class. So the difference between actor class and actor is similar to the difference between a class and object, right? In object, usually it's just a single object you declare, you use it. But if you declare a class, you can create multiple objects out of it by initialize it differently. So the same thing can be done for actors. There's actor class. You can give it extra parameter for initialization, and when you create it, you can just use the class name with some with the parameter it takes. Then this will create a new actor. And there's also a way, if you use actor class, it also gives some extra facilities for you to get the actor itself. So this is a notation you can use. You use equal self, then you're declaring self as a variable that will will be referenced to this actor after you create it. So after you create it, you can see here the self within this actor class methods. You can use self and convert it to the principal. And you can also use the same syntax we use for when we get the caller ID. We can get the caller, which is the installer of this actor or creator of this actor. Motoko has native support for stable variables, which is a facility to let you safely upgrade your canister. So when you declare stable variable, you just say stable var instead of var. And stable variables, you can also use pre-upgrade, declare pre-upgrade method and post-upgrade method, which is a system function in your canister. They can help translate those stable variables. So the thing here is my accounts. I remember user accounts with a tuple, with an array of tuples as a stable variable, so that when I upgrade my game, I don't lose all the registered accounts. But internally to the actor or to the canister, I actually use a more efficient representation for the players when I want to do the lookup. So I use two hash maps. So how this player's variable is constructed from the accounts, basically by computing these two hash maps. Then I use only players in my implementation. But when I want to upgrade, I need to convert from this player structure back to the account structure. So during pre-upgrade, I basically update the accounts with the latest set of players. So this is how I handle this persistence that survives upgrades in my game canister. So more on stable variables. There are two concepts in Motoko. One is like shared type. So by shared type, we mean things that can be shared between actors or between canisters. They typically have to be immutable data, but you can also include references and shared function references, actor references, but excluding reference to local functions and mutable data. So consider anything you can send from one actor to another actor. Those are considered as shared type. The difference between stable and shared is that stable is the same as shared, but allow mutable data, which is great for managing persistent state. So we can see some plain types like natural number, int, and text. They're stable. They're also immutable. They can be shared. But reference to local functions, they cannot be stable, because when you upgrade, your local function may change, right? You don't know the old reference now what it should be. And reference to actors or shared methods. So actors, basically, they're referenced by their principal ID, so which is why they can survive updates. And their shared method is basically a named function of the actor. So those are all kept as reference. And plain objects, as long as the object doesn't contain a local function reference, it's good to be considered stable. But this excludes objects that are constructed from classes. So when we construct object from a class, we typically associate a set of class functions to operate on this object. Those are local functions. So as we mentioned, during the upgrade, local functions may change. So which is the reason you cannot declare a object constructed from a class as a stable, which is perhaps a big bummer when people first get started with stable variables. So you can use array, but you cannot use things like buffer, because buffer is a class. There are ways it's not difficult to work around that, right? You can always save your buffer as an array when your pre-upgrade system function. You can implement that and load that from the buffer when your canister initializes. And yeah, basically the more general object type, they are not supported as stable variables. We also mentioned that canisters can call each other. So the way we call each other is that we need to declare those actors. But what if we only know their ID, right? We don't exactly know it may not be a local actor created from your Motoko program. It could be somebody else actor. So the simple way to declare that is that you declare an actor type with the interface you're concerned with. It might have other interfaces, but if you're only going to call this interface, you can just declare this method. For that actor, then this is a type, and it's constructed from just an actor call to the principal ID. So this is actually the NNS UI canister. It has this SCP2 cycles conversion rate method. You can later on call it just using an asynchronous call to get the result. If you don't need the result, the await basically denotes this as an asynchronous call. You have to wait for the result to come back to continue your program. We mentioned that actors, they execute one method at a time. So what happens when you are waiting, right? It actually, when you're waiting, it actually suspends this call. There's a local context of saving the stack and local variables, and this call will be suspended. Then your canister will be able to handle some other call. So before this await returns, your canister may be processing some other calls and may have changed the state. So be extra careful when you use this await. You cannot assume your actor global state have retained the same. Some variables, especially global variables, may have already changed their values. When this call to other canister returns, is actually another message. That's a reply message we get from a different canister, but it's handled almost in the same way as we handle incoming function call, which is also a message. So that reply, it gets delivered to your canister will wake up and resume from previously saved stack, suspended computation for this particular function. So you will continue from there. If you do a couple of this await, it means your thread of execution is gonna be suspended a couple times. And if you don't really care about the return result, right? You don't want to waste time of waiting for that. To do that, you can just say, I want to ignore the return result. This way, your thread of execution will not suspend. You will just continue from here. So atomicity is guaranteed on the message level, but it does not always translate to a single public function you declare for your Motoko program. Each message is handled atomically. So that means at any one time, only one of the method can run. It can be a previously suspended execution, which gets run when the reply message is received. But when the message is being processed, it's only single thread. There's no need for mutex or lock. State changes, they are persisted, and outgoing messages are sent only after this message is successfully processed. So that includes outgoing messages, which means if there's an exception, if you're somehow dividing by 0, right? If there's an error in your execution, this message handling will be aborted, and no outgoing messages will be sent. Despite that, you might have, if you use this ignore keyword to send message, you could have sent like tens of hundreds of messages, but later down the line, if your function has an error, all those messages will not be sent out. But if you use await, which means the current execution will end, then the pending messages will be sent successfully. So that's also when the state is persisted. When the error happens in WebAssembly, we call this trap. So when your WebAssembly code traps, basically means there's a irrecoverable error. All the state change to memory or global variables will be discarded. Nothing will be persisted. It's as if this call has never happened. The pending outgoing messages will just be dropped. An error response is returned to the caller. So yeah, something did happen. There will be an error response returned to the caller, and also whatever cycles your method has used, there will be accounted for. So that's when you have an error in your execution. Motoko provides some facility to help you handle this kind of asynchronous error handling. Let's look at this code. So we have two public methods. They are both asynchronous. The first one is stack. You basically minus the given value by 1. But if the given value is already 0, we cannot, because it's a natural number. If you deduct by 1, it will be an error, right? So we do assertion. So assertion in Motoko will trap. The other method, test, will basically just call Dapp using a wait to wait for its result to come back. And if anything happens in Dapp, if the call to Dapp traps, the test function will be resumed with an error response. So you can actually catch that error and use the debug. We can test locally to see what the error is about. You can do some other handling, like the return value here, which is return 0. The difference here is that we must know this try and catch is only for asynchronous error handling. This is a very big difference than the try and catch you might be familiar with other languages, like in Java or JavaScript. So here, if we declare this stack differently, not as an asynchronous call, but just as a function, a normal function. So it has the same thing that asserts v is greater than 0. If you call test, and test called Dapp, if n happens to be 0, then the execution traps, right? However, the catch will not be able to catch it because it's the current execution trap that's trapped. Catch here is only for asynchronous exception. So this trap is the current execution trap. But on the left-hand side, when we execute that, that trap is a different message. It's a separate message sent to your own canister. And that execution trapped, and you return an error reply. So that's why the catch is able to catch it over there. But on the right-hand side, this catch is not going to catch this trap. And when you call it from, let's say, when you're testing this from DFX, your DFX will actually report the error. So the trap is propagated back to the user. Well, on the left-hand side, the trap is handled locally by this function, and the user will get a success result, which is 0. So that's a very important difference between the error handling in Motoko and in traditional languages. You might be caught in surprise if you are not aware of this. So when you build your application, it gets bigger and you probably have many modules. A good practice is that you want to reuse somebody else's module, right? Maybe you want to use this SHA-256, which comes from somebody else's library. There is actually a package management tool we provide is called Vessel. You can use Vessel together with DFX. So you just need to create a vessel configuration file. Which is created by vessel init. It creates 2 files, and you can edit one of them to include the package you want to use. Here is SHA-256. And then you have to edit your dfx.json to say, well, when I build my Motoko program, I want to pass some extra flags. This flags is generated by running the command vessel sources, which will print a set of flags to be passed to the Motoko library to use. So you need to essentially need to download vessel. Probably you just need to download the binary and make sure the binary is installed in one of your paths, and then you can use dfx together with vessel. In your package, you can import this. Normally, when we use base library, this is mo:\base, right? But here we declare this, declare a new library, new package, which is SHA-256. You just use that there, and the capital case is a module provided by this library, by this package. You can import that module as into your Motoko source. Another good practice is to implement unit testing for your modules. When you have too many modules, you want to test each individually to make sure they are functioning correctly before you integrate them together, which is a common practice in almost all the programming languages. In Motoko, you can also do that. Christoph, Definitely Engineer, has provided a convenient testing library, which is called Motoko matchers. So here's the example of using the matcher. I won't go into detail, but the matcher, if you use vessel, matcher will be installed on default. So you can use that. And when you want to run this test, you can basically run this command line. This basically says vessel bin is a command that returns the path that point to a Motoko compiler, and you run it with an extra flag saying, I don't want to use the Internet Computer System API, but I want to map it to the local execution API, which is WASI system API. Very limited functionality is provided by this mapping. You can essentially do debug print and maybe a couple other things. But as long as you're mostly using Motoko features, not Internet Computer features, you can test this locally on your computer. So that's the end of my presentation. So some very useful resources. One thing I find very useful is the language guide. I think it's written in a fairly easy to understand manner. I encourage you to read it in full. It's not very long, but it has sections that are very helpful to understand some nuances in the language design, as well as how the language maps to the Internet Computer platform. And when you write programs, you want to use the base library. Base library is documented here, and also there are other guides like SDK, how to use SDK to compile Motoko and stuff like that. And we also have a growing collection of examples, which is in this repository. They have both Motoko and Rust examples. Some of the examples you make use of the more advanced features of Motoko, like actor class. So you can just clone this repository and play with the examples by yourself. And the last thing I want to mention is the Internet Computer Interface specification, which describes the system API to interface with this platform. So by system API, I mean is between the API between your canister and the system. There are a handful of APIs in there, not very difficult to understand. So I encourage you to read the spec, which helps you to understand what functionalities your actor actually has, your canister actually has access to. For example, the time library, right? If you want to get system time, the time is a little bit different on the internet computer platform. When you use it on your local system, you get very good precision. You may get close to real-time values. But on the internet computer, when you call this time function, it might return a slightly outdated time that is allowed to be different than real time. So there are other nuances that are not particular to Motoko itself, but when you use Motoko, you are using those library functions which may access those API. Understanding this API is very beneficial for you to understand your canister behavior. All right, that's end of my presentation. I'm open to any questions.
Okay, thank you so much, Paul. We actually do have a lot of questions. So let's dive right in. So first question, JS can call any canister on the IC from the front end. Can a Motoko canister do the same?
Yes, Motoko canister can call any other canister.
All right, so next question. So for stable variables, is it clear to developers that the object layout might change, and does the object layout refer to the memory layout of the variable?
Yes, it actually refers to the memory layout, which means a change in the Motoko compiler may trigger a change. So the compiler developers are very mindful about this. They want to introduce only compatible changes to stable object layouts. And another thing may change the layout is when you, for example, if you have a record of a couple fields in it, right? You might introduce new fields. Stable variables, you can change the type, you can add and remove fields, but they are subject to the subtyping rule in Motoko. Or the subtyping rule in Candid, actually. I didn't go into the detail here, but if you want to know more, you should read the discussion about subtypes in Motoko Guide, as well as in Candid. I would say the compiler is smart enough to do the check for you. So if you're not careful, you might worry you introduce incompatible changes to your stable variable, then you will screw up your canister state, right? When you do the upgrade. Motoko actually check that. The compiler is able to check that automatically, and will tell you when you are introducing an incompatible change to your stable variable. It will prevent you from compiling that program. But if you're doing Rust, I would encourage you to use Candid to check it. There are tools to check it, but it's not enforced. Apparently not. The Rust compiler doesn't even know about it, right? It won't enforce over there. But Motoko has this extra check to help you.
Could I just chime in here?
So we have Claudio from the languages team.
So some of those goals are aspirational. So Motoko at the moment doesn't verify whether your stable variables are compatible when you do an upgrade, although that's my next task on the list, and we always designed it with that in mind. There is a check to make sure that your interface has evolved in a compatible way, the external interface, not the stable variables, which you have to manually do with a tool. And I think DFX doesn't actually check that yet, but it can do in principle. And the other comment was one about stable variables. So the stable variables actually do have a compiler version independent format. So that means we deliberately designed the stable variable layout once serialized to stable memory so that it is compiler version independent. So you should be able to upgrade from a old canister built with one version of the compiler to a new canister built with a different version of the compiler. And even though the in-flight memory layout may have changed, for migration purposes, the temporary representation that's used is actually stable and shouldn't change. But maybe that's just confusing things.
Yeah, thanks, Claudio. I jumped the gun here. Sorry.
Oh, that's fine. That's fine. That's just to clarify.
Yeah, no worries. And thank you. Thanks, Claudio. Paul, the original asker of this question, also had a quick clarifying question. So does the layout matter to devs, since there aren't facilities in Motoko to directly manipulate memory addresses?
Yeah, I would say that's the safety feature, right? You cannot directly manipulate memory address, so that the compiler can do a lot more things. Like Claudio mentioned, you can make sure you choose a compatible format.
Yeah, so for Motoko, the memory layout isn't observable to the programmer, so we're free to change that. Interop with Rust. I mean, if you're going via Candid, that's the kind of interop layer that we provide at the moment, then you're okay, because Candid defines the kind of interchange format. That's the interface definition language, right? But if we ever try to link Rust and Motoko code in the same canister, then that opens up a whole other zoo of problems, and then it will be important. Yeah, but you can't do that at the moment.
Right. On that topic, actually, a trick I've been using is, if I really want to upgrade my canister, some stable variable, to an entirely different type, right? The way I do it is I name my variable as basically accounts _0, accounts _1. I introduce additional stable variables for the new format. Then in the pre-upgrade or post-upgrade, I basically convert from the previous stable variable to the new stable variable, so that I can port over all the states without worrying about losing that. So that's the trick I've been using. I basically have version that.
Cool. And I see a follow-up question from a different question asker on this topic. So this person is saying, I once deployed an application to the internet computer and was using a stable variable. And after updating my code, I lost my state. Is there a way to get some warning if you're going to break your state?
Yeah, go ahead, Claudio.
So at the moment, no, but in principle, yes, we're working on implementing that. That's actually priority number 1 at the moment.
Okay.
Yeah, it depends, right? It depends. I think some of the problem we run into is caused by the tools. For example, if you upgrade your canister while the canister is still running, you might have a bit of problem. So the tools needs to stop the canister first to make sure it no longer has pending messages to process. So sorry, pending reply. So means when it calls out to other canisters, it is still waiting for the reply. It has to wait until all those replies have been processed. Then there will be no longer incoming messages to your canister. Then that's a safe way to stop it. Safe point to stop it, and then you upgrade. So that measure has only been reinforced recently. But I do think there's still a bug somewhere. so yeah, it could be a fault of our implementation on the replica side. So I was testing this yesterday. I ran into problem. So although I'm pretty sure I have pending messages that I haven't received reply yet, but I was still able to stop the canister and upgrade it. So that was not a safe upgrade. So I end up losing some of the state. So that's something to be aware of. But I mean, losing state is pretty painful. So even your own application, if you're not careful with playing with the state, you might lose it during the upgrade. So I would strongly encourage, you implement a way to dump your state So as a backup, you can dump it to a binary blob, then you fetch it using DFX, something like that. Could be a good way to do that. I actually implement that for my reverse canister. I can back up all my user accounts. So that's just one suggestion.
Okay, thank you. Thank you, Paul. So next question, if query calls use multiple hardware threads, but replicas currently only run on one core, does that make sense?
Yeah, the update call essentially is because we want to follow the actor model, right? We don't want to break the actor model. If we allow concurrent execution of methods that both can mutate the state, then we're introducing non-determinism and perhaps even corrupt your canister state. So if we follow strictly the actor programming model, then execution that can mutate your state has only to be run in one thread. A way to avoid long-running methods that can block your execution is to break up your interface into finer grained steps. So that's yeah. So it has to do with actor programming model, but it also has to do with with the safety concern that we don't want users to bother with locks and mutex and all that, which can also be a easy way to shoot yourself in the foot.
Great, thank you, Paul. So next question, can a canister call its own public methods without creating an actor reference to itself? Will these methods be called async or sync?
Yeah, it can call its own method. So you can call its own method if it's just a local method, you just call it, right? So it doesn't create a separate message to send to the canister. But if it's a public method, so at the moment, all public method has to be async. If you call it, it will be an asynchronous call. You have to wait for it. If you didn't declare it as, well, if it doesn't have any return type, you can skip the return type for your method. Then you can call it. Then it's treated as a straight call. It's like the system will just add ignore for you, so you don't wait for the result to come back. But if you declare a return type as :async, then parentheses, then that's async. That's definitely async call. You have to explicitly use ignore. But if you skip that declaration, you can just call it.
Thank you, Paul. So next question, will canisters always be single-threaded in order to preserve this actor model? Do you envision multi-threading in the future, or can true parallelism only be achieved using a multi-canister architecture?
I guess the key property we want to preserve is for your execution to be deterministic. So introducing threads is not actually a conflicting goal for preserving the actor model. So actor model is on the surface, right? It's interaction with outside world. It has to process one message at a time. But internally, when you are processing that message, there could be multi-threaded parallel constraints for you to use, as long as they produce deterministic result. Then the execution, the replicated execution, so-called, basically means when we compute your canister state, we compute it on every node that's participating in the consensus. They have to run this same message in the same way in order to produce a result state. The result state has to match with the state computed by other nodes, so that we know they can reach consensus. They all perform this execution correctly. So the number one criteria is to be deterministic. But as long as something is deterministic, we don't rule out the possibility of introducing like multi-threaded execution or parallel execution in the future. So yeah, that's something we want to explore.
Thank you, Paul. And then next question, are there facilities in Motoko to handle futures or promises like JavaScript? So for example, promise.all.
Right, yeah, that's a very good question. So far, we don't have it, but if Claudio is still here, maybe he can he can chime in.
Claudio is indeed still here. Claudio, do you want to take this one?
No, we don't have any combinators like that. I mean, we do have promises. The async type is basically a future, but we don't have the combinators for doing wait many. Well, wait many is actually, that's fine. It's the racy one that we can't do at the moment. So wait for the first one to complete and ignore the rest. It's in the back of our mind. There's no, I think we could do it. We haven't so far.
Cool. So the next question is actually a double question. So first question, can you get the principle of the caller when doing a query call without it becoming an update call? So when adding the message to the shared, when designated the function as a query, it does not compile. And then second question, is there a way to get the caller for the whole canister without having to add a check to all of the functions in the canister?
The first question, you definitely can do that. I've been doing that. So yeah, probably your syntax is a bit off. You have to say public shared, then with a message in parentheses, then function, right? You have to remember there's a func keyword there. Then you, query, then function, then parameters. So yeah, I guess it was just some syntax issue that prevented from compiling. Perhaps you can ask a question on the forum. Some of us can look at it for you. Now on the second question, I don't think there's a way at the moment. So when I showed this example of actor class, right here, the actor class. So you do get a shared message, right? So, but that message only refers to the installation message. It's not referring to, you cannot get a caller of each invocation of your method. You have to annotate each of the method individually with a shared part.
Cool. So I know we're coming up at time. So one final question. Theoretically, could we connect a front end not hosted on the internet computer with JavaScript to a canister on the internet computer?
Yes, you can do that. If you use the JavaScript agent library, you can definitely do that. So that has nothing to do with, I mean, there's no restriction. You can use Agent.js or use the Rust agent. They can all talk to canisters on the internet computer basically from any program. The most straightforward model is that we provide facility to just host your website on the internet computer. But if you're building a native app, you're welcome to use any of our libraries to directly talk to canisters.
Okay, great. Thank you, Paul. And just as an FYI for Paul and Claudio, there is a request in the Q&A to add documentation on how to write and run unit tests of the docs, especially that example with Motoko matchers that you had on your slide, Paul. I know that we are at time, so let's wrap up. So Paul, thank you so much for this talk on how to build a Dapp and Motoko on the internet computer. Thank you to the community for tuning in and for Claudio for assisting Paul with the questions as well. So we will see you all next time at a future community conversation. Bye everyone, take care.